Welcome back. We can use SK image, scikit image, or the built-in various type of filters to apply them on images. For example, this classic cameraman image. We can extract the edges of the cameraman by using a special type of filter that is called a Sobel filter. And once we give an image as input, what the operation does is that it gives out this image, which essentially detects the edges of the cameraman in this case. So we know what an edge kernel looks like, right? So we know that it looks something like this. So this is, each of these numbers is going to be divided by 9. So the corresponding filter that we actually use is something like this matrix over here. So you've got minus 36 by 9, which is minus 4, and then you can have 1, 1, 1, and 1. And once you multiply it with the corresponding image, the central pixel is going to be, first we take the average of all the surrounding pixels of a given pixel, and then we subtract the value of the central pixel by multiplying it with 4. So it's essentially taking it gives us an idea of how different a central pixel is from its neighboring pixels. And if it is significantly different, then that means we are at an edge location. That's why we see brighter values when we convolve a given image with this edge filter. Okay, what we are going to do is not use sklearn. We're going to do it the hard way. It's going to be seemingly difficult in the beginning, but it's going to help us in understanding how these convolution neural networks work and finding Waldo ultimately. Okay, so what we do is we have our kernel over here, right? And what I'm going to do is I'm going to write a function that takes this kernel as input and applies it on a given image. And we are going to use these built-in functions in PyTorch because we want to use it for deep learning later, right? So what we do is first we convert the given input kernel from NumPy to Torch or PyTorch tensors. And then we simply, what we do is we do a convolution of that particular input or given input image with the kernel that we have. And then we are going to return that output. I welcome you to take a look at different aspects of this code. This is essentially a hack of the built-in convolution operator that is present in PyTorch. Now we know why PyTorch is special, right? It allows us to run code on GPUs, and it has automatic differentiation built into it. It allows us to do all sorts of optimizations really efficiently, okay? And we want to use that perhaps, and but our real goal is just to understand that, or make sure that we can do a correlation or a convolution within PyTorch. So we have a kernel over here, we have got an image over here. I create a filter object, I set the kernel, so I initialize that filter to this particular kernel value, which we know is the edge kernel. It's the same matrix that we had, that we discussed earlier, with the -4 in the middle and ones all on the sides. Okay, so we know this gives us edges, at least in SK image it does. And what happens if we do it over here? And that's what we're going to do. We're going to simply apply that filter, set the kernel, and then perform this convolution. If you do that, and I have already given you the code, if you do that, this convolution results in this edge image. So that's pretty cool. So we can do convolutions in PyTorch, right? So that is going to be a good step in understanding how we can find Waldo using convolution neural networks, right? But let's ask the interesting question. Can we, so let's backtrack actually a little. We've seen that once you convolve a given image with a filter, you get another image at the output, right? And that's interesting. That means we can process images using these filters. But is it possible to design a filter or to make a filter that allows us to find Waldo? So, or do anything useful with it, like try to identify. So rather than us knowing what filter we want, can we use PyTorch and our given training data set to learn a filter that would help us in locating Waldo when we convolve that particular filter with the given input image? So that's what we are going to do next. And we are going to take a very simple example. Rather than finding Waldo, which is a large image, and then we don't have that much training data available to me, at least I'm going to take a very toy problem to go to that to the solution of that bigger problem. Let's say we've got this as an input image. So it's a very simple image. All of it is white, and then we have got pluses and minuses at different locations. And our goal is to identify these pluses and produce an output target image by convolving it with a filter, this input image with a filter that is not known to me, so that the output image produces these dots at the location where we have those pluses. We can threshold it, and there are simpler solutions, but those really don't help us in understanding or generalizing to what we are going to do next. Let's say finding Wold or finding cancer cells in a given input image. So this is our input. We know what our output or target image looks like. All we don't know is the filter. Ideally, like my dream here, or the task I have set out to do is, can we design a filter based on this training data that allows me to find these pluses or the locations of those pluses, not only in this image, but ideally in other similar images. Okay, so that's what we are going to do next. If we try to solve this problem using a multilayer perceptron, let's say the input image size in this case is 122 by 200, and so the number of inputs, if we use a fully connected neural network, is going to be 24400, and the target image size, in which we have the locations of the pluses as single white pixels and everything else is black, the number of dimensions for that is also going to be pretty large. So the number of weights that we are going to end up is going to be huge. And if you add hidden layers on top of that, then good luck. It's going to be very difficult to find anything to train a neural network to do this, fully connected neural network to do this. So instead, what we do is we fall back to our basics, right? What we do is, instead of using a fully connected neural network, what we want to find a filter, or a kernel K in this case, so that when I convolve this kernel with the given input image using this particular operation, which you know now is already available to us in PyTorch, right? And we can use the built-in convolution operation of PyTorch to perform this representation. So the input is essentially this image I, the output is image H. The parameters of this particular machine learning model are going to be these weights K that we don't know. And if we use a matrix of size 5 by 5 or a filter of size 5 by 5, then we essentially have a total of 25 parameters that we want to find. We don't know what goes at these different values, so that when I convolve this particular input image with my target, I can essentially produce an output that has these white spots where there were pluses originally. Okay, so that's what I want to do. So that is the representation bit. We are going to use a 5 by 5 kernel. We are going to convolve that kernel with an input image that we're going to take, and we're going to produce an output. The next thing is evaluation. Like any machine learning problem, for a given input image, we have a corresponding target image that is given to us, right? We know that each pixel value is in this target image, and then we have the corresponding input image, the corresponding output from our machine learning model. We can use this pairwise difference, or mean square error, as this is simply mean square error. We can use that as a loss function. And then the problem becomes, essentially, we want to minimize this error function with respect to the different values of K. And that is what we are going to do next using PyTorch. And this is the code that allows you to solve this problem. Let's say we have again input image over here. We have a corresponding target image that I'm creating, because I know for the given input where the object is. So I do that, and then I use the same filter that we had implemented earlier. But instead of just using the filter now, what we are going to do is we are going to use an optimizer, so that when I pass this input image X through this filter, the output and the target match up. And that's what this code over here does. So we are going to do a number of iterations. What I'm going to do is we're going to pass the torched version of the input, so that it's a tensor. we're going to pass it through the image, through the filter F that we've created over here. We're going to compute the output. We're going to, let's say we can even apply a sigmoid on the output if we want, like to make it non-linear. You can even use linear operations, but in this case I'm using a sigmoid. So you do the convolution. Let's say you got an input image, you do a convolution, and then you apply a sigmoid on top of that as an activation to each pixel. So that's what this operation is going to do. The next thing I'm going to do is simply measure the loss. So this is the representation bit, the implementation of the representation bit. This is the evaluation, and this bit over here is the optimization. So at the end of this process, once I've gone through this, I'm going to end up with a filter which, when I convolve it with my input image and apply a sigmoid on top of that, is going to give me those dots where I've placed them. And you're welcome to run that. For that particular input image, what we ended up is an output like this, which has these, at the location of the pluses, there are these bright white spots. And as you can see, there are some low values where we had those minus signs in the input image. Okay, and what we can do is simply thresholding this input image, and we're going to end up with the locations of the dots. That's pretty cool, right? So this is how you can use convolution to find pluses or to find Waldo, right? So essentially what all of this is doing is we are convolving a given input image with a filter, which is being learned now through optimization. And when we convolve that filter with the input image, we get an output that is close to our targets. So that's the whole process. This is the filter that is output. Notice that this is simply a 5x5 matrix. And if you look at it a bit closely, it has this thing, a white pixel over here and a white pixel over here along the vertical, right? And then it has this black thing in the middle. So that kind of looks like, if you differentiate between pluses and minuses, this is the difference between the plus and a minus, right? A plus looks like this, a minus looks like this. So this thing that we have found over here in the pixel is actually a vertical line that we are trying to identify, right? So what it's essentially looking for, or the filter that we have generated, would produce a positive response at the output. If a top pixel is positive, the bottom pixel is positive, but not on the sides. So that is what a vertical line looks like. And essentially, instead of detecting positive signs, we have made a filter that detects these vertical lines, and then we can use that to detect our plus signs. So that's how you can use, it's a very simple, I think this is it's the simplest convolution neural network that you can make in PyTorch or in any other case. Remember, the goal is, instead of finding all those weights, we just have a single weight matrix which is getting convolved with the whole of the input image and producing this output. So have fun with this. The code is already available to you, and I welcome you to play with it and try to identify whether you can detect other shapes. Perhaps you can extend it to detect Waldo wherever they are. Okay. And next time, what we're going to do is we're going to take a more structured look at how these convolution neural networks actually function, or how you can build even better ones, more powerful ones than the one that, or the basic one that we made right now. Thank you.